Today we have transport 2, homework number 2. In this problem today, we have a 10 centimeter long container split up 50-50, with half of the side contains pure water, H2O, and then the other side contains half deuterium, DTO. And so what's going to happen today is that we're going to pull that barrier, remove that barrier, and then I've already drawn the profiles of what would happen. So those two species are going to diffuse together. So after 0.1 second, we're going to have a little bit of diffusion as it starts. And then we're going to look at the profile after 60 seconds, denoted right here. And then after an infinite amount of time, concluding that they are going to be diffused together fully, and it will be a uniform species. At the very end, uniform, where the deuterium and water is spread evenly. And what we're trying to find today is the overall mass flux, the first thing we're trying to find, denoted by N here, after 0.1 seconds, after everything goes together. And then number 2, we want to estimate the order of magnitude for the driving force of diffusion at this particular time point. And then finally, we're going to sketch some plots for the transport profiles for each of these separate time slots. So again, it's after 0.1 seconds, right after the barrier is flipped, after 60 seconds, and then after an infinite amount of time where everything will be uniform. So, like I said, the first thing that we're going to be solving for is the overall mass flux, denoted by little n. I want to make a note, this is different than the overall mass diffusive flux, which is denoted by little j, you can recall from the last video. And to make this problem easier, we have our molecular weights for both water, H2O, and deuterium, D2O here, and then we also have the densities of water and the density of deuterium to make this a little bit easier. And then, as well as that, we have at the 0.1 second time slot, we're given the overall, the max molar diffusive flux, and that is 2.78. So this is again different than the overall, the molar flux, which is denoted by big N, and the equation for that is big N is equal to, an I of a species, is equal to Ji plus the concentration of I times the molar velocity. And since we are only dealing with, we're not dealing with any flow rates or anything like that, we're in a closed container here, we can remove this. We cannot take it, we don't need to take it into account the concentration because the molar velocity is 0. So because the molar velocity is 0, that means that the molar flux is actually equal to the molar diffusive flux. And because the overall diffusive flux, molar diffusive flux, is 0, and it is 0 because if you have X amount of material going that way, X amount of H2O going that way, then you're going to have the exact same amount of DTO, deuterium, going that way. So because of that, the overall molar flux is 0. You're not going to have moles or something on this side versus this side. And because of that, we can treat these as equal and opposites. So the molar diffusive flux of water is going to be 2.78 moles per meter squared times second, and then the overall, the molar diffusive flux of deuterium is going to be negative 2.8 moles per meter squared second. And because of that, that makes it really easy, because if J of H is that, then this must mean that the molar flux of H is also equal to 2.78 moles per, and then moles meters squared times second, and that means that as well the molar flux of deuterium is also negative 2.78 moles per meter squared second. So because of all this, we have all this, and then we can use the next formula, which is just going to take our molar flux to mass flux, because that's what we're trying to solve in the first place. And the relationship between moles and mass is obviously just the molecular weight. We have grams per mole, mass per mole. So by to transfer this, the molar flux to the mass flux, we can take NH is equal to little n, is equal to the molecular weight of water times capital NH, which is the molar weight. Because if you have, the moles are going to cancel out, the units are going to cancel out. So by plugging stuff in, we have 18 grams per mole times 2.78. That is going to give you a number I will find in a second. And then likewise with deuterium, the mass the mass flux of deuterium is going to equal to the molecular weight of deuterium, which is going to be 20 grams per mole, times negative 2.78, which is the molar flow. So I'm going to plug these numbers. After plugging the numbers, we can see that the mass flux for water is 50.04 grams per meter squared per second, and then the mass flux for deuterium is negative 55.6 grams per meter per second. So that means that this is the amount going this way, and this is the amount of deuterium going that way. But what we wanted to find was the overall mass flux, and in order to find the overall mass flux, we simply just sum these two. So we have 50 and overall is equal to 50.04 minus, because it's a negative sign, 55.6, and of course this is in the units of grams per meters per second. This comes out to be negative 5.56 grams per meter squared per second. And so what this means is the overall mass flux is that there's a 5.56 grams per meter squared per cubed per second of material going that way. And if you think about it, this really makes sense, because if you have a heavier substance right here, it's heavier in both molecular weight and density. So if you have a heavier substance here and you have more of it going to the left, then obviously the overall, if you had it on a scale, it's going to shift that way. So obviously if you have a heavier substance here and you pull it and it diffuses that way, the scales are going to shift in that direction. So that makes sense for our overall mass flux, negative 5.56 grams per meter cubed per second. Perfect. So that was part one. We ended up with a total of negative 5.56 grams per meters cubed per second. The second thing we're going to do is estimate the order of magnitude for the driving force of diffusion when the time is at this time slot right here, positive 0.1 seconds. The first thing I'm going to do is write out the definition of the driving force. The driving force of I is equal to the sum of the molar fraction of I times the molar diffusive flux of J minus molar diffusive flux of I times the molar fraction of J. And this is all over concentration of I plus our little diffusivity constant right here of I and J. Well, we have a couple of unknowns here, but if you recall back to the last problem, the sum of the molar diffusive fluxes are equal to 0, which means that Ji is equal to negative Jj. So we can substitute that in there, and then we also know that for molar fractions, xi plus xj is equal to 1, which means that xj is equal to 1 minus xi. So what we're going to do, we're going to substitute those two values in here, and we're going to get the driving force is equal to, I just want to also note out that this definition is for multi-component systems, and we're only dealing with two things here, so I can get rid of that sum sign. So I'm going to have the molar ratio of I, and then by substituting this stuff in here, we're going to get negative Ji, correct, minus Ji, and 1 minus xi. So after we're going to FOIL that guy out. Give me a second to do the algebra. And, oh, I forgot, this is all over the concentration of I, and then the diffusive constant of I and J as well. So, after this is also the same thing. Concentration of I. Perfect. Well, if you see, these two terms cancel out, so we get the definition for this problem. The driving force is equal to the negative molar diffusive flux of I over the concentration of I, and the driving force of J. Well, we have this guy. This guy is what we were given to up there. And then this guy, so for liquids, it's 10 to the negative 9 meters squared per second. This is the diffusivity constant. And for liquids, we can guess that it's in the range of 10 to the negative 9. Well, the other thing that we don't have is this concentration right here. And in order to get that concentration, I'm going to break down what it is a little bit. I'm going to separate this stuff off. The concentration is equal to moles per volume, the moles per volume total. So we're going to try to do the concentration for the entire, we want to find the order of magnitude for the driving force. So we're going to do the entire concentration over the entire thing. So basically, let me erase these eyes as well, these aren't needed. Basically, so concentration is moles over volume total. Well, we're not given moles, especially for the entire thing, but what we are given is what we are given is grams per mole. So we can deduce from this that moles can be converted to mass over molecular weight over volume from total. We also don't have mass, but what we do have is the density. And for the density is in the units of mass over volume. And what we're going to assume is that the volume for each side is 1 meter cubed. We know that the length is that, but we don't know the width. So what we're going to do is assume that there's 1 meter cubed of H2O here and 1 meter cubed of deuterium right there. And by making that, it simplifies our density equation in that this is just 1, and that we can plug in our mass for each of these to be 1,000 and 1,100. So what I'm going to do is the total C is going to equal, I'm going to substitute in the masses right here, it's 1,000 divided by 0.018, because that's in grams per mole, so we need to divide that out so that our units are consistent, and then that's going to be divided by 2 plus the deuterium side of it, all divided by 2. This is all divided by 2 because it's the total volume. 1 cubic meter equals 2 cubic meters. That's what we're dividing this by right here. So when you do the math and multiply this all out, you get an answer of 55,578 moles per liter. So this is our C. We now know what the C is. We now know what the diffusivity constant is. It's 10 to the negative 9 for liquid diffusion. And we know the molar diffusive flux from what we were given at the beginning. So because you know all these things, we can now plug everything into our lovely equation. So the driving force is equal to, I'm going to use a negative sign for the molar diffusive flux because deuterium is diffusing that way. So you get the molar diffusive flux over the concentration times the driving force for liquids, and when you multiply this all out, you get an answer of about 55,000, or just, no, sorry, you get an answer of about 50,000 moles per meter cubed. And so this is basically, it's about 50,000 and like 20 or something like that when you multiply this out. So we can simplify this so that our order of magnitude for the driving force of diffusion is about 50,000 moles per meter cubed. So this is our order of magnitude. This is the answer to the second problem. So if you recall, the last part of this homework problem was that we need to sketch the plots for various mass transport profiles. And so what we basically have here is our density profile over time from our 3 distinct areas. We have at t equals 1 second, t equals 60 seconds, and then an infinite amount of time when they're all diffused together and we have a uniform substance. So what we're looking for, we have a density profile, the molar concentration profile, the molar diffusive flux profile, and the overall mass flux profile for these 3 times for each. So basically what I'm going to go through is explain how I got to each of these values. So what we have first is the initial density function. The densities are going to be, the graphs are going to be pretty much the same. We have our boundary line right here at 5. I probably could have made this a little bit more drastic, but you still get the picture, as that nothing has fully diffused yet, so you can still see that the density is still pure H2O. And I also want you guys to realize that this is up a little bit because the densities of water and the densities of deuterium are still different. Density of water is 1,000 kilograms per meter cubed, and the deuterium is 1,100 kilograms per meter cubed. So that's why they start off at a little bit different spots, and that the density is not exactly in the middle, it's up just a tiny bit. You can't really tell from this graph, but that's what it would be. In the intermediate phase, it's just a little bit more of a slope. It's not as drastic because there's been time for both materials to kind of diffuse into their respective areas. And then finally, The density for H2O is going to level out at exactly half because everything's just split up into two areas now. You have half of the water is going to be on this side and half of the water is going to be on this side. So the density is going to be what we started with divided by 2. So 500, and that would be 550 for the deuterium. For molar concentration, we get a number of 55 by coming over to here. Here's our work from, it's very similar to the work from problem 2, and that concentration is a function of mass over molecular weight over the total volume. And by doing the calculations, we find that the molarity, the moles per liter, starts at 55.6 for water and 55 for deuterium. So they're pretty much exactly the same. You won't be able to tell from this graph. But similarly to the density, they're going to both diffuse down. They're going to have the exact same middle point because the moles are going to, there's going to be X amount of moles on both sides because we have very similar molar diffusion. And then at T equals 60 seconds, like in density, it's just going to be a little bit more, like a little bit less drastic of a slope because both materials have had time to diffuse together a little bit. And then at T equals infinity, when we have a uniform substance, there's going to be just complete uniformness throughout the entire system. So both are going to have the same molar concentration, and it's going to be exactly half of what we started with. For molar diffusive flux, we were given at the very beginning that the molar diffusive flux at point 1 is 2.78 moles per meter cubed per second. So that's what we were given here. And then as we get to the middle, they're obviously starting to diffuse a little bit. So the rate of the diffusive flux is going to be higher. It's going to be in the positive direction because water is moving to the right. That's what I denoted the positive direction. And then deuterium is going to be negative because it's moving towards the left. As you can see, the very top of that crest there is at 2.78 because that's what we were giving as the max molar diffusive flux at 0.1 seconds. At 60 seconds, it's going to be a little bit, again, of a smoother surface because it's now had time to diffuse throughout the entire system. And as you can see, that peak right there never reaches the peak that we initially had because it will never diffuse as much as that. At T equals infinity at a uniform substance, neither one are diffusing, so it's just going to be constant at 0 because it's already uniform. In terms of the overall mass flux, here's our graph right here. This is basically the problem 1 that we did. So when we found N at the very beginning, we found that to be negative 5.56 grams per meter cubed per second. So as you can see, we're coming down here, and then it strongly dips right there to 5.56 seconds, then comes back up. The reason why it stays negative and never comes back is because deuterium has a higher density than water. So whenever, like I said earlier in problem 1, whenever the heavier substance is moving left, it's going to kind of tip the scales a little bit. So it's going to have that negative overall mass flux. At 60 seconds, we have the same exact thing over, only it's just a little bit less obvious and we never reached that full-on peak of negative 5.56 seconds. At an infinite time, as we have a uniform substance, our 0, we're going to have an overall mass flux of 0 as nothing else is happening anymore. So this concludes problem 2. We have found the overall mass flux, N. It is negative 5.56 grams per meter cubed per second. We have estimated an order of magnitude for the driving force, about 50,000. And here are the lovely sketch plots for our mass transport profiles.